All right, yeah. Thank you so much for the introduction. Yeah, great to be here virtually. And yeah, as you said, please do interrupt at any point if you have questions. I'm happy to, chat about whatever is interesting to you. And yeah, this is really joint work with mostly my PhD student, Yang Song. He is amazing. He's on the job market this year. So if you are looking for somebody in ML, please do interview him. I think you're not going to regret it. So, all right, let's jump right in. Let's see when this works. All right. So, as you might have heard in the last few years, there's been a lot of progress in building generative models of a variety of complex objects like images, text, video, music, molecules, materials. It's really exciting that we can build computer systems that can generate these complicated objects. And you can see here some of the results from an OpenAI system where you can generate images based on text prompt. And it's pretty impressive that you can build a system that can generate images with this kind of quality based on a high level description of the scene. And, of course, it's not just images. In text, there's been a lot of progress in building language models, which you can think of as generative models of text, pre-training these large language models on a lot of unlabeled text has proven to be a really powerful way of improving NLP systems. And it's kind of like now common practice and necessary to achieve state-of-the-art results on a lot of tasks. And these models, again, they're not perfect, but they can generate reasonable text. If you start a sentence with something like, you take a GPT model and you start saying generative models cannot, it will complete it with something like this. It cannot be considered to be an adequate representation of reality. So maybe they know what they don't know. And and more generally, I think it's really an exciting area in machine learning right now. This idea of building a foundation model, of building some kind of model that can take advantage of a lot of unlabeled data, and because it can generate it, then hopefully that means that these models are understanding something about the structure of the data, and we can use this as a strategy to then quickly, either pre-train models to get features or quickly figure out how to adapt them then in a few short way to new tasks. And this has proven to be very effective in text. It's starting to show very much a lot of progress in images, and I think we can potentially extend these kind of ideas to a lot of different modalities. So how do generative models work? Well, there are kind of like two main classes of generative models. The first one are implicit models, where essentially the model represents directly the sampling procedure that you use to produce samples, let's say generate images. Perhaps the most famous class of implicit models are things like generative adversarial networks, where the method essentially starts from random noise sampled from some simple distribution like a Gaussian, then transforms it using a neural network into a sample. And essentially you can choose any neural network that will define a valid sampling procedure, and the goal is to figure out one, make a choice for the weights for the neural network so that it produces samples of high quality. And so you can essentially choose any architecture that you want, which is great. It's a very expressive kind of like family of samplers. They tend to work pretty well in practice. One of the challenges is that it's very hard to evaluate the probability that the model would output a particular sample, which means that it's typically not possible to train these models by maximum likelihood. And so it's also difficult to, you have to use adversarial techniques with discriminators. It's hard to do principal model comparisons to figure out which one fits the data better. So the alternative is more classic explicit models, where you essentially model directly the probability density or the probability mass function P of X. So you essentially build a model that for that function that takes an input and tells you how likely that input is under the model. And a probability density function or probability mass function is a complicated object when it's over high dimensional spaces. There's been a lot of literature in the last many decades on ways to represent these objects compactly, either using ideas from graphical models like Bayesian networks, undirected models, or more modern approaches using neural networks like deep autoregressive models, flow models, and so forth. The key advantage is that because you're representing directly the likelihood or the probability density function, you can easily get access to the probability that the model assigns to any particular input, which means you can train it by maximum likelihood. The challenge is that probability density function, is not negative, which is easy to enforce, but it also has to be normalized, has to integrate to 1. And that is kind of like the key challenge. You cannot choose an arbitrary neural network to represent the mapping. And there is always kind of trade-offs between how expressive that function is, which is something you need if you want to model a complicated data set, and the fact that either it has to be normalized by design, or you have to be able to somehow use approximate inference procedures to be able to sample from it or evaluate likelihoods. So in this talk, I will present some of the work we've been doing, which is essentially a new class of generative models that where the object that we're going to model is not the probability density function itself, but it's going to be the score of, which is essentially the formula that you see here, which is the gradient of the log density with respect to its input dimensions, right? And so now this is called the score, the time score. And note, this is not the gradient with respect to the model parameters, the one you've seen probably over and over, and that you use for training. This is the gradient with respect to the input dimensions, right? So it's a vector that tells you essentially in which direction you should what's the direction that you should follow if you want to increase, let's say, the log density as fast as possible in a particular point at each point. So visually, it would look something like this. So this object, this score is a vector field. And so if you have a density px, which is just a mixture of two Gaussians, shown here, there's one mode on the top right, one mode at the bottom left, and you can see them here. Hopefully, you see my pointer. And given this density, you can compute the gradient at every point, and that is the score. And so, as you would expect, it's kind of like a vector field. You can see all these arrows that are kind of like pointing towards the two modes of the distribution. So if you like analogies with physics, this is kind of like thinking about an electric potential versus an electric field. They're kind of like similar objects, but there might be situations where you want to work with one versus the other. So why should we use scores instead of working directly with the log density? Well, the key thing here is that something strange is happening here. I think, give me a second. I think there might be some. Okay, this is better. Why do we want to use scores? Well, as we discussed before, the thing is that we want to model a probability density function, which for every x, it tells you the probability. We want this probability density function to be as expressive as possible. We want it to be a complicated function, but it has to be normalized. And so what this means is that the area under the curve has to be 1. So for example, if you want to use a neural network to model this function, it's easy to make it non-negative. But then, if you choose an arbitrary neural network, you will need to compute the area under the curve, and you would have to normalize by that normalization constant, the partition function, if you've seen it before. And in general, computing the area under the curve becomes expensive in high dimensions. And so that's why essentially directly modeling the likelihood is potentially complicated. On the other hand, if you look at the gradient of that expression, which is in this case just a one-dimensional function in 1D, we see that is a simpler kind of like expression. If you take the log of the expression on the left, you're going to have two terms. You're going to have the energy essentially, and then the log partition function, log z. And the nice thing about looking at the score is that if you take the derivative with respect to x, the gradient, the log partition function term disappears because it's a constant with respect to x. And so intuitively, you can see the scores provide a easier way to parameterize probabilistic model, because the score function is a lot less constrained. Essentially, you don't have to worry about the area under the curve. In 1D, essentially any function will define a valid score. And so to the extent that you can work directly with the score instead of working directly with the probability density function, it's a lot easier to parameterize these models. So now, what is the basic challenge if we want to work with score models is, well, the first thing we need to do is we need to figure out how to estimate them from data, because we no longer have access to the probability density function. We cannot work directly with maximum likelihood. And so we need to figure out different ways of estimating scores from data or doing learning. And so the basic problem we have is one where we want to essentially do density estimation. So there is an underlying data generating process, P data shown here. This is unknown. You get to see a bunch of samples from this probability density function. And I should mention, because we're working with scores, we're working with gradients, these methods are only applicable to continuous random variables. And so let's say that we have a set of training examples from this distribution that are sampled IID. Then the question becomes, how do we estimate the underlying vector field of scores? How do we figure out what is a good approximation of the true underlying vector field of scores? And so we need to come up with a model, which is a vector valued function as data that at every point will give us an estimate of what is the gradient at that point, what is the direction that we should follow if we want to increase the log likelihood as fast as possible. So that's the goal, come up with this good approximation. And of course, the challenge is we only have access to training data. We don't know analytically what the underlying data distribution is. And so more formally, this is the problem. We're given a set of IID samples from some unknown data density, P data. And the goal is to estimate its score, the true vector field of scores. And to do that, we're going to define a model family, which is a set of vector valued functions that at every point will give us the estimated gradient. And the first question is, well, we need to figure out a performance metric. Given that you have a score model, how do we figure out whether it's any good? And intuitively, it's good if it's a good approximation to the true vector field of scores. And so we have two vector field of scores. We have the true one and we have the one coming out from the model. How do we compare these two objects? And a natural way to do it is to, basically overlap them. And then at every point, look at what is the difference between the true gradient and the estimated gradient, and then reduce everything, let's say, to a scalar by taking the average over the whole space. And then, if the vector field are similar, then the difference will be small, and so the average will also be small. So that's the Fischer divergence. The formula is the one you see here. So we take an expectation with respect to the data distribution of the L2 norm between the difference between the true gradient at every point and the estimated gradient. And of course, this is a reasonable objective. If we can drive this to zero, then it means that our model is perfect as data matches the true gradient at every point. However, it seems like it's not an objective that we can evaluate, let alone optimize as a function of data, because recall, we don't know analytically what P data is. We only have access to a bunch of samples. So it might seem that we're stuck because we cannot optimize this as a function of data. However, it's possible to show that if you apply integration by parts to that expression, or just expand the square and literally apply integration by parts, this objective is equivalent up to a constant to the objective that you see in the following line, where we basically have two terms. It's still an expectation with respect to the data, but now the objective involves two terms. It involves the square of the L2 norm, basically, of S theta squared, and then the trace of the Jacobian of S theta. And the key advantage here is that it no longer depends on things we don't know. It only depends on properties, basically on our model, on its data, which are things that we can in principle compute. Still, of course, it involves an expectation with respect to the data distribution that we can't quite evaluate, because the only thing we have access to are samples. But for that part, that's easy. We can always come up with a Monte Carlo approximation, and we always need to do that for any kind of learning objective. We can approximate the expectation with a sample average, so we can just basically evaluate that objective on the data points that we have on the xi, and then average. So that's great, because now we have an objective that we can optimize. One challenge is that it does involve the trace of the Jacobian, which is something you can compute. You can do it with backpropagation, but it can be expensive in practice when you're dealing with high dimensional, when D is large, when the dimensionality of the data is large. To see that, let's say that we have a deep score model. So this is a vector valued function. It takes X and it maps it to a score, which is another vector, has the same dimension as the input. And we need to compute two terms. We need to compute the L2 norm of S theta, which is easy to do. You basically can just do it through one forward pass in the model. The trickier part is the trace of the Jacobian. Jacobian is basically this matrix of partial derivatives, where you need to take the partial derivative of each output with respect to each input. And how do we do that? Well, naively, if you wanted to compute, let's say, and if we want to compute the trace, then it's basically the sum of the elements of the diagonal. And so, in order to do that, we will need to compute that term, the partial derivative of the first output with respect to the first input. And to do that, naively, you would have to evaluate one forward pass and then take one backward pass to compute the partial derivative with respect to that input. And to get the second element on the diagonal, you would have to do one forward pass and one back propagation, and so forth. So to do it naively, it would require something like order D back propagations, which is horribly expensive if you have when D is large. So if you're trying to model high dimensional data, this will not work. So that term is problematic, and that's what essentially makes vanilla score matching not really scalable to high dimensional data sets. So how can we make progress? Well, one way to do this is to is something we call sliced score matching. And the intuition here is that one-dimensional problems are usually easy to handle. And so perhaps we can make progress by applying random projections to this vector field. So intuitively, remember what we're trying to do is we're trying to compare these two vector fields, the model and the true one. And these are, at every point, we have a vector. Instead, what we could try to do is we could pick a few random directions and then project the model and the true score along these directions, and then compare the random projections. And the random projections are all essentially one-dimensional problems for which we can, the trace of the Jacobian should be easy, right? Because there is no, the matrix is basically just a scalar. So that's the intuition. Essentially, what it boils down to is a variant of the Fischer divergence objective that we saw before, where what we do is, again, we compute essentially the L2 norm of the difference between the model and the true score. But before we take a random projection with respect to some random direction V. And it turns out that, again, there is a term here that appears to be something we cannot evaluate because it depends on the true score. But you can still apply integration by parts, and you can reduce it to an objective that only depends on the model. Here, S theta is just the gradient of the log of the density. So it's the same as before. And it turns out that this objective is scalable because basically we now have Jacobian vector products, which are essentially like directional derivatives that you can compute easily via backpropagation. It turns out that this objective still has the nice theoretical properties that we had before. So if you try to do learning based on slice score matching instead of score matching, you still get consistent estimators for any choice of the number of random projections that you apply at every point, as long as you use at least one. And you also get nice properties like asymptotic normality for the estimator that you obtain by optimizing the slice score matching objective. However, the key advantage is that it's very scalable. This is a plot kind of like showing the scalability of different methods as a function of the data dimensionality, kind of like showing the seconds that it takes per iteration to compute these losses. And you can see that in brown here, that if you look at vanilla score matching, it's kind of like scales linearly with the data dimension, and at some point it breaks down and you don't have enough memory, it doesn't even work. However, slice score matching in blue is actually very scalable, and you can use it on very high dimensional data sets without problems, because we're doing these projections. Now that we have solved this problem of estimating the scores, we can finally build a generative model. So the pipeline is something like this. We start from some data samples from some unknown data distribution. And then we use slice score matching, or there are alternative methods like denoising score matching to try to estimate the true underlying vector field of scores and come up with this model as data, which should hopefully be a good approximation of the true vector field. Now the question is, well, how do we use this gradient information, right? If we had access to the likelihood, then maybe we would know how to generate new samples or to evaluate probabilities. How do we do inference when the only thing we have access to is the gradient of the log density, right? Clearly, the gradient captures a lot of information about what is the shape of the true density, but how do we use it to, let's say, generate new samples? And so the intuition is that the gradients are basically telling us the direction that we should follow if we want to increase the log likelihood as fast as possible. So you can think about, well, perhaps we can use some kind of like local procedure where we initialize particles at random. Then we can try to essentially follow these arrows, follow the gradients, and that should increase the probability of the samples. And indeed, if you do that, then you see something that looks like this, where you will move the particles towards the modes in this example, where we have just two modes, a mixture of two Gaussians. Now that's good, but it's not quite what we want. We would like to be able to sample from this probability density. And how do we do that? Well, it turns out that a variant of this idea, the idea that we've just discussed, following the scores, would basically get stuck in a local optimum. So it will not explore, it will not generate real samples from the data distribution. However, there is a way to change this procedure by a little bit. Essentially, what you do is, instead of just following the gradients, you follow the gradients plus a little bit of noise. So you do noisy gradient ascent. And that gives you a Markov chain Monte Carlo sampling method known as Langevin dynamics, which is known under some regularity conditions, under some assumptions to, in the limit, if you keep running this procedure for long enough, it will produce samples from the density corresponding to that vector field of scores. So to the extent that your vector field of scores is close to the true data density, then you're going to get a reasonable sampler. And so that's kind of like the procedure. You want to be able to sample from a data density when you only have access to the score. And this is what you would do it. You would initialize a sample any way you want based on some initial distribution. And then you would just repeat this procedure where you would just do gradient ascent plus a little bit of Gaussian noise. And the gradient is estimated using the score model. And this is kind of like the full pipeline. So you start with samples, you estimate the scores, and then you produce samples using Langevin dynamics. And here, the challenge with this approach is that the way we are not using the true vector field of scores to run Langevin dynamics. We're using an approximation that we've learned via score matching. And it turns out that the quality of this approximation can be poor in certain regions of the space. And intuitively, if you think about the objective, we are estimating this objective using Monte Carlo samples, using a Monte Carlo procedure, right? Based on samples, based on a training set. And if you think about it, kind of like we are basically seeing a bunch of VAEs samples, and most of the samples will come from high data density regions, right? They will be close to the two modes of the distribution in our simple example. And so we're using that local information to kind of like figure out what is the gradient at that point, what is the direction that you should follow. And intuitively, you're going to see most of your data coming from high data density regions, and you're not going to get a whole lot of signal when you're far away from the high data density regions. And which means that look at the estimated scores versus the true scores, they're going to be pretty accurate, close to the high data density regions, but they can be very inaccurate when you're far away from the modes of the distribution. Right, you see here that there is the true data scores for this mixture of Gaussians shown here, and there's the estimated ones on the right. And you can see that the arrows are pretty accurate in these two regions, close to the modes, but they're very inaccurate when you're far away. They're pointing in the wrong direction, basically, because we're not getting data around those points when we do it from samples. And so the challenge is that if you think about what Langevin and CMC will do is you will start the procedure somewhere, maybe based on a uniform distribution, based on a Gaussian or something. And initially, it will be pretty far away from the high data density regions, and we're kind of trying to go there. The problem is that the arrows that the algorithm is following, they're not going to be accurate. And so it will have a lot of trouble exploring these low data density regions and will not be able to find its way towards the modes of the distribution. So how do we fix this problem? Well, the idea is that if we were to add noise to the data density, just convolve it with a Gaussian, then the resulting perturbed distribution would be kind of like supported over the whole space. Now we would see samples from this perturbed data density all over the space, and which means that we would be able to estimate the scores of this noise perturbed data density all over the space. So that's good, because it would mean that if we follow these arrows, we're going to be able to get good directional information. Langevin and CMC will work. The challenge is that we're no longer sampling from the distribution we want, the data density, the one that looks like this. We're going to be sampling from some other distribution, this perturbed data density, which is not quite what we want, right? Unless the noise is small, this perturbed data density is not going to be a good approximation of the true data density. And so, yeah, we're going to be able to sample, but we're not sampling from the right distribution. So the solution is to think about a sequence of noise levels, going from small to large, from left to right. And intuitively, you can see that essentially the more noise you add, you can see it here visually on this particular image of a dog, the more noise you add, the more structure you're destroying in the image, the more the sample looks like noise. It's distributed all over the space. It looks like, let's say, a Gaussian if you're adding Gaussian noise, regardless basically what kind of distribution you started from. If you had enough noise, you're basically going to go back to, let's say, a Gaussian distribution. And the idea is that instead of focusing on a single noise level, where we have this trade-off between how accurately we can estimate the vector field and how good of an approximation it is, right? If we were to use a lot of noise, like the one on the right, yeah, sure, we would be able to get the vector field, but then that doesn't look like an image. And so instead, what we do is we essentially use we try to estimate all the vector field of scores corresponding to all these data densities perturbed with increasingly large amounts of noise. So we have a single conditional score network, noise conditional score network, that will take as input X and a noise level, and we'll try to estimate the vector field corresponding to the data density perturbed with Gaussian noise with that intensity sigma. And so there's going to be a single model that will try to come up with an estimate of all these vector fields, which are going to be different because we're adding different amounts of noise. We can estimate each one of them using slide score matching or some kind of score matching objective that we see here, where we're basically trying to estimate how close we're minimizing some kind of Fischer divergence between the model and the data score and the data score for the data density perturbed with Gaussian noise of intensity sigma 1. Then we have maybe some scaling factor that is kind of like weighting how much we care about accuracy at different noise intensities. We train this model, we get a good estimate, hopefully, of all the vector fields corresponding to different noise intensities. Then the way we're going to use it for inference is using something called annealed Langevin dynamics, where intuitively what we can do is we can start by initializing our particles any way we want, let's say based on some Gaussian distribution with large noise. Then what we do is we follow the gradients for the data density perturbed with large amounts of noise, which should be a good approximation with the pretty close to the distribution that we use to initialize our Markov chain Monte Carlo sampling procedure. Now, this sample are not what we want. There's too much noise. We would be kind of like sampling from images like the one you see on the top right, where there's too much noise. So what we do then is we use these samples to initialize another Markov chain, Langevin chain, corresponding to a data density perturbed with a smaller amount of noise. And again, we follow this procedure. And then we use these samples to initialize another Markov chain corresponding to the data density perturbed with an even smaller amount of noise. And at this point, if the noise level is small enough, we're sampling from something that is pretty close to the true data density. And hopefully this procedure will work because essentially as long as these densities, these noise levels are not too different, then samples from the previous chains are going to be a good approximation. They're already pretty close to the high data density regions. And so at that point, the directional information that we get from our score model will be good enough to increase the quality of the samples even more, right? You can think of this procedure essentially some kind of denoising, where we're progressively removing noise from the samples and making them closer and closer to a true data sample, like a true image of a dog. And so that's what the procedure looks like. Here's an example of the sampling procedure of this annealed Langevin dynamics procedure on a few image data sets that you might recognize. You can see that we start with the white noise, and then we are progressively essentially denoising it by following the gradients of these estimated data densities. Using the score model that we estimated using the score models trained by score matching. And we are progressively basically denoising them and following the gradients and going towards high data density regions. And eventually we get back some clean samples that kind of look like the ones we could have used for training the data set. I see maybe questions? Yeah, I'm happy to take questions.
Yes, I think there's a question from Andre. The question is, do you have a sense of how many temperatures you need as a function of the number of modes?
So the question, how many temperatures you need, we'll see. Indeed, that is kind of like a hyperparameter that is a little bit annoying to set. And we have we have a NURIPS paper where we explored this, both essentially analyzing some toy examples, some simple mixture of Gaussians kind of examples, and we worked out what is the optimal kind of like number of temperatures that you need or noise scales. And we've shown that this kind of suggested or recommended settings, they work pretty well in practice. What I'll show next is that you can actually get rid of that hyperparameter to some extent by looking at an infinite number of noise levels. And so we'll see that that's a pretty clean way to get around this problem of selecting the right number of noise intensities. Other questions? All right, and yeah, so here you can see some other results that you can get from this procedure on higher resolution images. As you can see, these are pretty high quality samples that are produced by a model which is not a GAN. So that's pretty encouraging. Very exciting that we are able to generate samples of this quality with a model that is probabilistic in nature. We're really estimating a gradient of a log density, and to some extent, we have an object that is very similar to a probability density function, except we're working directly with the gradient, but implicitly we're actually working with a really fully probabilistic model. And turns out that we can do even better. And the way to do it is to consider an infinite number of noise scales, just as I mentioned before. So you can think of this process as of adding noise, as basically, you have samples from some data distribution, a mixture of two Gaussians shown here. And then what we're doing is, we're perturbing it with increasingly large amounts of noise, and generating these intermediate noise perturbed densities, of which we are estimating the scores, the underlying vector field of scores. In this case, this is all one-dimensional, but of course, this is just for visualization purposes. And intuitively, what happens is that, after adding sufficiently large amount of noise, no matter what kind of data distribution you started with, you're going to destroy all the structure, and the signal to noise will be extremely small. And then if you add sufficiently large amount of Gaussian noise, then it's this, no matter what kind of Gaussian distribution you started from, you're going to get back with you're going to be left just with noise. And so it's just like basically sampling directly from the noise distribution. As you see from the right, you're kind of like interpolating from the data distribution towards a distribution that is entirely noise. Now here we're doing this process with basically four bridges. You might wonder, well, and this is basically generating these noise perturbed distributions in between. But why don't we look at more noise distributions? Like what happens if we choose an intensity sigma 1 that is kind of like in between 0 and sigma 2, or sigma 3 that is in between sigma 2 and sigma 4? Well, there's going to be some perturbed distribution corresponding to the noise intensity that is kind of like going to be an interpolation between these two. And indeed, you can kind of like think about a continuous sequence of distributions interpolated which is basically are going to be denoted PT, which is basically going to be the data distribution that has been perturbed with noise of a certain intensity, where now the index is continuous. So it's no longer discrete, but we have a full spectrum, a full continuous spectrum of data distributions perturbed with increasingly large amounts of noise. But again, capital T is basically pure noise. We're going from left to right here, we're destroying the structure in the data and going from a data sample to pure noise. And so, this is kind of like what it looks like for an image. You kind of like start with a sample that is, let's say, an image, and then you increasingly add noise and you completely destroy the structure. And you can think about the procedure of essentially adding noise to you can think about a procedure to sample from this sequence of distributions. And you can describe that with a stochastic differential equation, where basically you start, let me show you again this, you start with a clean sample, and then you add increasingly large amounts of noise. If you do that, following this very simple stochastic differential equation that you see here, it's not super important what the formula means, but it just means that you basically define the stochastic process where you start from data and add noise over time, and critically, this is a continuous process. Now, why are we doing this? Why are we describing this with a stochastic differential equation? The reason is that it's possible to define an inverse stochastic differential equation that corresponds to the process of going from noise to samples. Now here the axes are reversed. We have noise on the left and we have samples, we have data on the right. There's going to be another SDE that captures the process of going from noise, from some noise prior to data. And it turns out, so it goes from noise to samples, like exactly the same procedure we were using before when we were using annealed Langevin dynamics to sample. And so here you see kind of like what is the inverse SDE. It's basically a sampling procedure for a generative model, right? You start with noise, and then you progressively denoise it into an image, right? And you can think of each of these paths being a trajectory, a solution of an SDE. And critically, it turns out that you can work out analytically what is the stochastic differential equation corresponding to the reverse process of adding noise, of going from noise to data. And it turns out that it has a relatively simple analytical form. And the critical thing that you need to know in order to be able to characterize this reverse time SDE is the score of the noise perturbed data densities that you have in this sequence of that are indexed by T, right, by the noise level. So just like before, kind of like the critical element, the thing that we need in order to define this SDE are this vector field of scores that are now not just a finite sequence corresponding to some arbitrarily chosen noise levels. Now there's an infinite number of noise perturbed data densities, and we need to somehow be able to estimate the scores of all of them if we want to characterize this inverse SDE. If we can do it, if we can estimate these scores, which we can do using score matching, then we have a new kind of generative model where we can basically sample. Instead of sampling by a neo-Langevin dynamics, we can basically estimate this pink term, the vector field of scores. And then you can use any SDE solver to essentially produce samples from this generative model. As long as you know this term, then everything else is known. Sigma squared here is just basically a term that determines how much noise we add over time. If you have that, then you can solve the SDE and you can produce samples from the model. Right, that's the score function. And so that's kind of like the idea of using an SDE to define a generative model. We have a forward SDE that goes from data to noise, where we're simply just adding noise to each data sample. This is a very simple kind of SDE to sample from because we're just basically adding noise to the data. And then, just like before, the key thing is that we can characterize the reverse SDE, the process of going from noise to set data, and we can characterize it in closed form. And the only thing that we need is basically this score function. So the idea is that we can estimate the score function from using score matching, and then we can sample from this SDE. And it turns out that this can further increase the quality of the samples. Here you can see some results from, well, this is no longer in submission to iClear. This was presented at iClear this year. And you can see some of the high resolution image samples that we can produce using this model. And it turns out that this is actually producing state-of-the-art results on some data sets. You can actually beat GANs, generative adversarial networks, in terms of sample quality. Which is very exciting because it's one of the first times that we're able to beat GANs in terms of image quality using a completely new kind of architecture and and type of generative model. And given all the engineering that went into GANs and all the many years of people trying different architectures and different things, it's very exciting that we were able to improve over that with a completely different approach. And here you can see some of the results, like in terms of FID scores, inception scores. If you believe this kind of metrics, we're able to do better. Just qualitatively, if you look at the samples, these are very high quality samples that we can generate using this model. Another advantage of this procedure is that you can also define an equivalent ordinary differential equation that you can use to sample from this from a stochastic process that has the same marginal as the reverse SDE. So now the difference between the previous SDE was that the dynamics before were stochastic. It's a stochastic differential equation. We can define a dynamical system where the dynamics are deterministic. There is no longer any noise here. We have a purely deterministic kind of like evolution for this trajectory. Again, that can be described in terms of the these score models. You still need to know the score models, but if you know the score models, basically it's possible to define an ordinary differential equation that you can use to, again, sample from these kind of distributions. And this is nice for several reasons. First of all, once you have the scores, which are estimated via score matching, then you can use, you can define the SDE, the ODE, which is now a neural ODE, because it's defining, the dynamics are defined by a neural network, which are these noise conditional score models. If you have the ODE, then you can use any black box ODE solver to solve it. And you can trade off compute for accuracy in the solution of the ODE. And here you can see some of the examples that we get by sampling from a model trained by score matching, by solving the corresponding ODE that goes from noise to data. And you can trade off compute by basically saying, okay, how many neural function evaluations you want to do. And the more you do, the better the quality, the more accurate the solution to the ODE is, but more expensive it is. I mean, you can really trade off compute for accuracy. I see questions. Yeah.
Stefano, there are two questions. First one is from Kashif. The question is, do you think it's possible to have progressively growing score matching networks? Any thoughts about if that is even possible?
It might be possible. I mean, at the level of the architecture, in NCSM++, we actually borrowed some of the architectural choices that people did in progressive growing of GANs and things like that. It might be possible to, even from a more probabilistic perspective, kind of like have a hierarchy of models where you're sort of like modeling more coarse and fine kind of aspects of the scores. I think it'd be interesting to think about it. I think it should be possible.
Right. The second question is from Michael. Are there any challenges with image resolution as it is increased? Like for instance, sampling time compared to the GAN models?
Yeah, great question. Yeah, that is the bottleneck. At the moment, sampling time is much slower compared to a generative adversarial network. So that's why there is so much work, and we were trying hard to see, okay, are there ways to make sampling more efficient by using better ODE solvers, better SDE solvers? Are there ways to accelerating the sampling procedure even more? I think these models have these nice properties that in some sense inference and training are decoupled. So training is very scalable because you can kind of like train all the score models separately. They're all kind of like trainable independently. And after but the procedure that you use to sample is kind of like decoupled. Like it's in a GAN, the procedure that you use to generate samples is the same at training time, at test time. Here, the procedure that you use for generating samples is different. Like you can even plug in different samplers, different ODE solvers, different SDE solvers, and they will all sort of work. And you can even choose how much compute budget you want to allocate at test time. So I found it exciting that it actually this works, because yeah, it enables all kinds of trade-offs in terms of sort of like how much compute you want to put in and the kind of accuracies that you want to get. So it's exciting that we're no longer tied to this idea that whatever procedure you use at test time for inference, it has to be the same that you use for training, otherwise it's not going to work. It's exciting that it's actually possible to decouple those two things. But at the moment, yeah, even with the best kind of like samplers we have, it's still slower than GANs. So that is one of the limitations of this approach.
Cool. Yeah, sorry, there are a few more questions, it seems.
Yeah.
So some questions from Ashwini. The first one is, how sensitive is the noise conditional score networks to the exact values of noise used while training the network? And the second question is mode collapse observed in these kind of networks? And the third question is, I guess, somewhat related to what you just said, like the speed, but maybe just the mode collapse and the sensitivity question.
So mode collapse, it doesn't look like they do, and I'll show you later that the reason they don't seem to have a whole lot of noise of mode collapse is that it turns out that there is a way to train these models or there is a relationship between training these models via score matching and maximum likelihood training. So it turns out that there is a way to choose the weighting in the, we have that mixture of score matching objectives where each component in the mixture corresponds to a noise intensity, and you're kind of like jointly trying to estimate about all these score models, all the score vector fields. Turns out that there is a way to choose these weighting components so that you're actually essentially optimizing a lower bound on the likelihood of the data. And so from that perspective, it's not surprising maybe that there is no mode collapse, because it's more like a variation of autoencoder or an autoregressive model where we're really doing maximum likelihood. So there is an incentive to be mode covering. So if I have time, I'll try to maybe go through those slides quickly. The other question is sensitivity to the noise levels. I'm not sure I understood in what sense. So we do train the network for all possible basically noise levels by Monte Carlo sampling over different noise intensities and trying to estimate the score at that noise intensity. Then at test time, I mean, it's possible that by following this SDE, because there are errors, we're basically not denoising the samples by the right amount, and so there's kind of like a mismatch between the noise that the samples have during sampling and the one that they should have if we had perfect scores. And that's potentially a problem. I've seen some papers where they are trying to kind of like estimate what is the actual amount of noise that the samples have, so that you can use the right noise conditional score model to figure out how to denoise it. You kind of like trying to figure out what is the real amount of noise intensity that you have left on the samples. And they were able to improve the results by a little bit. We didn't have to do it. And I guess to the extent that your score models are sufficiently accurate, that shouldn't be a problem.
Cool. Apparently 3 more questions. First one is it clear what aspect of the data the SDE version helps with? Like, for instance, have you tried simple synthetic data like low-dimensional manifolds like spheres or mixtures of well-separated Gaussians?
So that's a good question. We definitely did some synthetic experiments at the beginning just to make sure the method was working. But I think that we don't have a great intuition, I think, for what exactly is the method helping with, except that, there is this interpretation that the moment you go to continuous time, there is a maximum likelihood interpretation, and so perhaps that's what's helping. There's basically a way to think about these models as a VAE effectively, with an infinite number of latent variables, like a continuous. You can think of like a continuous hierarchy of latent variables indexed by time, where time is continuous, and so that might be the reason that these methods are actually improving.
The other question is about the intuition of why score-based generative models can generalize to new samples instead of learning something like very trivial, like, I don't know, a simple GMM around the training samples.
Yeah, that's a great question. I mean, we still have the problem of overfitting. So in principle, we're still optimizing based on samples, and so if you were to just optimize the Fischer divergence or the sliced Fischer divergence based on samples, in theory, the optimal solution is to basically just memorize the training set. We haven't experienced too much overfitting. And the good thing that, the nice thing about this kind of fully probabilistic model is that you can actually use a test set, or you can use a validation set to kind of like check what the loss look like. And you can detect and potentially prevent overfitting. Unlike again, like we have a proper scoring rule that we're using to train a model, and so we can actually do principal model comparisons based on that objective function.
Mm-hmm. Another question from Pradeep. So with regards to annealing, if the score estimates with lower noise intensity remain poor in low density regions, then even if I had good samples, when we add high noise, would it help for sampling with lower noise intensity?
Could you repeat the question?
Yeah, so it's about annealing. If the score estimates with lower noise intensity remain poor in low density regions, then even if you had like, good samples when we add those high noise, would it help for sampling with the lower noise intensity?
So yeah. So the issue is that, yeah, for the low noise, basically, we're not going to get good directions when we're far away from the high data density regions. The thing is, by using the annealing procedure, basically, we're going to initialize our let's say the final Langevin chain with samples that are already pretty close to what they should look like, because they are coming out from a previous sequence of annealing chains. And so we're not actually going to be ever visiting these low data density regions. And so in practice, we are only ever needing the scores in the regions where they are accurate. And so that's the intuition for why the procedure might be working.
Yep. Hopefully that answers your question.
Yeah, thanks.
All right, Stefano, you can probably go ahead with the talk.
How much time do I have? It looks
like some people may have left at 1 p.m. for other meetings, but you can keep talking. We don't have a strict time limit, actually.
All right. So what's give me 5 minutes, 10 minutes?
Yeah, like 5 to 10 minutes would be great.
Right. So maybe, yeah, I just wanted to mention that. Yeah. So one of the this connection with maximum likelihood, I think, is pretty interesting. So first of all, one of the advantages of thinking of it from the perspective of ODE, so an ordinary differential equation, is that now you can essentially think of this as a continuous time flow model. So at this point, if you think about the ODE, you're essentially sampling from so some prior distribution, some Gaussian, which is or this distribution that you would get basically by taking the data and adding a lot of noise, which is kind of like the same as sampling from the prior. And then there's this deterministic evolution, which you get by solving the ODE that would give you a sample. And this mapping is invertible, and so it is really like a continuous time normalizing flow. And it's possible to evaluate likelihoods exactly through the change of variable formula. So given a sample that comes out from this probability flow ODE, you can actually evaluate what was the probability of generating the sample through this sampling procedure. And it turns out that even though these models are trained by score matching, the likelihoods that you get are actually extremely good. Like they are better than any flow models that were explicitly trained by maximum likelihood. So not only you get very high sample quality, but you also get very good likelihoods on this kind of image data sets, which is interesting. And the reason is something that we figured out in a paper that's going to be appearing in NeurIPS. It turns out that basically there is a connection between training by score matching and maximum likelihood. So if you look at that training objective that you see here on the right that we've been using to train these models, where we have all these noise perturbed data densities, and then we're kind of like jointly trying to estimate the scores of all of them. And there's some coefficient that we use to kind of like choose how much we care about the different noise intensities. It turns out that there is a choice of weighting that gives you an upper bound such that this objective function that we were optimizing by doing score matching is actually an upper bound to the KL divergence between the data and this probability distribution that you get by solving the reverse SDE. And so, and yeah, then there's a KL term, which is basically just the difference between the prior that you use to initialize the SDE and what you would get if you were to take the data and add a lot of noise, but that's almost zero if you had a sufficiently large amount of noise. And so the key thing is that, and like in a VAE, you can basically also per data point evaluate a lower bound on the likelihood assigned by the model to that particular data point. And kind of like the intuition is that you can think of the path of the SDE as a latent variable. and you can compute a evidence lower bound like, through variational inference. And effectively, that's what this, and there is a way to choose the weightings in the score matching, in this mixture of score matching objectives, so that optimizing that is the same as optimizing an evidence lower bound in a variational autoencoder. And so this, you can also think of these kind of models as latent variable models, where you have like an infinite, continuous time indexed hierarchy of latent variables, which basically corresponds to the samples that have been perturbed by adding increasingly large amount of noise. Or you can think of it as the path of the SDE that gives you that particular X as a latent variable. And so that's cool because then you can train these models by maximum likelihood. Like before, we were kind of like choosing this coefficient kind of like heuristically. But you know, if you actually choose it in the right way, so the only thing you change is basically change that coefficient so that the objective corresponds to a bound of maximum likelihood. You can further improve these likelihood numbers, which are getting, you know, now you're optimizing for likelihood instead of optimizing for something else. And you can further improve the scores that you get on these image data sets, which is pretty cool. And in fact, there is another paper by Google, also hopefully appearing in NeurIPS, where they come up independently with the same results, and they were able to get even better numbers with kind of like different architectural choices. And so another cool thing you can do that maybe I'll just mention it briefly is that you can also do controllable generation because we have this fully probabilistic model. If you use it as a prior over, let's say, what kind of images are likely a priori, you can combine it with some kind of like likelihood model that relates an image to some kind of measurement Y. And you can, in principle, try to use these kind of models to sample from the posterior. And the way to do it is that if you look at the posterior or the score of the posterior, it's going to have two terms. There's one coming from the prior, and there is one coming from the likelihood. And you know, we can use that as a score for the prior. You can use something estimated using one of these score models. And let's say you know the likelihood, then you know that's something that is specified by domain knowledge, and maybe it's a classifier that maps X to a label. If that's fixed, you know, you can compute this gradient, you can get that component of the score. And then in principle, you can use Langevin dynamics to try to sample from this vector field of scores where you have the prior, but you're also kind of like trying to make X consistent with the measurements with Y, so that you're also making the likelihood term basically happy. And you can use this to do a lot of things. You can use it to do painting, colorizations, class conditional generation, and you know, here you can see some examples here. And you take an unconditional score model that gives you a prior what images are likely a priori. You couple it with a classifier that maps X to a label Y. And then you try to sample from the posterior, and you can use it to do class conditional generation. If you have some kind of measurement, P of Y given X relates an image X to some kind of measurement, like masked version of the image. Again, you can plug it in, you can do painting, you can do colorization. And the cool thing is that these are not models trained for that particular task. You just take a pre-trained noise conditional score model for the prior, you couple it with different likelihoods, and you can get pretty good results. These are not state-of-the-art results, but they're pretty good. And it just works out of the box, right, without requiring any additional training. Here's more colorization results. And you can even do synthesis and editing. This is actually a collaboration with Junian here at CMU. And you know, you can use these kind of models to do fun things. Like you can start with a stroke-based painting, and then you can use it to turn it into an image, or you can start with a like something like this, and then you can turn it into a photorealistic image that kind of has the shape of that particular paint, of that stroke paint that you started with. Yeah, so maybe I think I'm out of time, so I'll just end here. You know, I think the key message is, yeah, think about this new class of generative models based on scores. They are nice because you can plug in whatever architecture you want for the scores. You don't have to worry about normalizations being invertible. You can train it by score matching, which means no minimax optimizations. They are stable. You're optimizing a proper scoring rule. So they're nice theoretically, and they work in practice. They give you high sample quality, comparable, better than GANs in many cases, which is very exciting, given all the engineering that went into GANs. It also allows for exact likelihood computation. That's very exciting. There are these connections with maximum likelihood, I think, are very interesting. You can achieve very good results also in terms of likelihoods using these models. And you can also use them to do conditional generation and editing. We're doing some fun stuff on inverse problems, like MRI kind of things where you have a measurement, which is kind of like a projection of the signal, and then you can try to reconstruct it. And this method seems to work extremely well in that case as well. So yeah, I think there's going to be a lot of exciting applications, just like for GANs, where I think you can probably swap in a GAN for this, and hopefully you can get some interesting results. And yeah, I think that's it. Sorry for going over time.
All right, no worries. Thanks, Stefano, for the great talk. Are there any questions? Okay, I already see some questions. So let's maybe deal with the questions first, and we'll try to give you a virtual round of applause after that.
Sounds good.
Yeah, the first one is, what if the score cannot be computed at all, for instance, on the discrete data?
Yeah, that's like, so as I said, like in principle, these models can only be applied to continuous random variables because the scores are not defined otherwise. In practice, you can think about, let's say, adding noise, basically dequantize your discrete distribution, and at that point, even if you add a small amount of noise, then that becomes continuous, and then you can apply score models. And so in practice, that shouldn't be too much of a problem.
The other question from Kashif is, what could be some open problems here?
Yeah, I mean, I think making sampling faster is certainly an open problem here. Is it possible to achieve kind of like sampling speeds that are comparable to GANs? I think we don't know whether that's possible. There are many new modalities that people haven't necessarily looked at, where people have, I think you can probably write a bunch of interesting papers just trying to apply these models to new modalities. I think there is still some theoretical questions, just get a better understanding of why these models work, whether the some kind of rates, how many samples do you need, what's the role of inductive biases. I think these density estimation problems are fundamentally hard. So to me, it's somewhat surprising that these methods work at all. And so why is that the case? I think we're not particularly close to getting an answer to that, and that would be very interesting.
Cool. Are there any other questions, comments, feedbacks? Okay, one more. Can score matching techniques be applied to datasets which have non-IID noise?
So the noise would be, are you thinking of the noise being added as part of this procedure of kind of like making the data distribution easier to model, or are you thinking of just that the data is measured with noise and you have to deal with it?
Yeah, Dushyant, maybe you can unmute and directly ask.
Hi.
Okay.
Yeah, I was thinking of the second case, but also the first case. I mean, the second case where the measurement noise is non-IID, but I guess you can also maybe add non-IID noise as well.
Yeah, I think that's also a potentially interesting extension or direction. Like at the moment, we're basically essentially adding Gaussian noise to interpolate between some simple, from the data distribution to some simple prior. And the reason is that we know that there are some connections between denoising and estimating with respect to a Gaussian noise distribution and estimating the score, basically. But there could be other kind of mechanisms of basically destroying the structure and then trying to reconstruct it in a reverse process. There might be other choices that work better than what we're doing right now. Back to your first question, I don't think there should be a problem if the data is measured with non-IID noise. In fact, I mean, I think the whole method here is useful to capture complicated dependencies. I mean, if you think about an image, like all the pixels are related to each other in potentially very complicated ways. and the model is doing its job at trying to figure out what those relationships are. And so whether you think of that as being a property of the data distribution or coming from the measurement process, I think that shouldn't be too much of a problem.
Thank you.
Thank you. Any other questions? All right. If there's no questions, please, I'd like to invite everyone to just join me in a virtual round of applause. We could just do the reaction thing on Zoom. Yeah, we do hope to, like, sometime hope to host you in person once the pandemic ends. Hopefully we can visit CMU.
Yeah, I would love to.
Yeah. Great. If there's no question, just as a reminder for everyone, we're meeting again at the same time next week for a talk on adversarial robustness. But other than that, thanks everyone. Thank you especially to Stefano for the awesome talk and for participating in the talk today. All right.
Thank you so much. Yeah.
Thank you, Stefano.